Welcome to the third hour of User Interface Strategies 93. Joining me for this hour is Dr. Tom Furness of the University of Washington. For 25 years, a leader and initiator in developing what's become known as virtual reality. He's currently also a co-editor of the new journal called Presence, Teleoperators and Virtual Environments. And he'll be giving us the latest about virtual reality. Tom?
Thank you, Ben. Thank you, everyone, for being here today. I'm delighted. To my friends out on the West Coast, I imagine it's still morning there, but we're happy to have you as well. What I'd like to do today is tell you about the future of human-computer interfaces. Indeed, the kind of things that we're talking about in virtual reality are highly developmental. But we hope in the near future that there will be indeed many industrial and business applications of this technology. What I would like to do in my hour is to start off with some observations that we've made about humans over the years. Now, you have to understand that my background came out of the Department of Defense, and for 23 years I was trying to develop interfaces primarily for fighter pilots and advanced airplanes. So my bent is a little bit different than perhaps the normal business computer applications, but we think some of the principles still apply. I'd like to discuss then, after we understand about humans, some problems with current computer interfaces. How virtual interfaces then can help, some definitions that you have in your packages about virtual interfaces. I won't really cover all of those, you can read those yourselves. How these virtual interfaces work, and some applications, and where the industry is going, and perhaps where do we go from here. To begin with, let's talk about humans. We have to understand, of course, that basically humans are three-dimensional beings. We see things and we hear things and we touch things in 3 dimensions. This is the way our architecture is wired. Indeed, from birth, we go about discovering the world. And we're able now to build an understanding and even indeed models of this world that we could keep with us throughout our lives as a result of these early experiences and even later experiences that we have in our lives. Another thing that we have to understand about humans that we don't think about too much is that we basically have 2 visual systems. Now, these visual systems operate in conjunction with each other. I must apologize for this glare that's on the slide, but this particular slide characterizes what I mean by the 2 visual systems. Basically, there are 2 types of receptors in the eye. There's what we call the cone receptors, which are contained in the fovea of the eye, and then there are the rod receptors that are primarily contained in the peripheral retina. Now, these 2 receptor regions are hooked up in a way that it really, the visual inputs that we have are processed in 2 different portions of the brain. The focal visual system, which is really mediated by the fovea of the retina, tells us sort of the what of things. That's the detailed vision. Whereas the ambient visual system, which is mediated by the peripheral retina, tells us the where of things. Now, it's important for the what to know where to look. So therefore, we have these 2 visual systems that work in conjunction with each other. And this becomes very important when we're concentrating on building computer-human interfaces, because we want to have the optimum way to search these visual spaces to input information into our visual cortex. Another thing we have to understand about humans is that we're really all different. We grow up in different backgrounds, different cultures perhaps. We have different shapes and sizes, skills, even different interests. And yet the way we seem to build interfaces, we expect everyone to be the same. As a matter of fact, someday I hope we change the word from user interface to participant interface, because we need to treat everyone as an individual, having a separate model perhaps in his or her head in interacting with this world. To give you an example of this, I'd like for everyone, both here in the studio and out there in the world, to clasp your hands. Now, how many of you have your thumb on the top, your left thumb on the top? Raise your hands, please. Okay, now assume that, how about the ones that have right thumb on the top? Raise your hands. Now, how many of you have neither thumb on top? Well, okay, we have one. Usually we have at least in the Six Sigma, we have one person that does that. Very good. Uh, now, I'd like for everyone to fold your arms, please. Now, how many of you have your right arm on the top? Okay, and I assume that the rest of you have your left arm on the top. Now, what I'd like for you to do is to keep your arms folded. Now, reverse it. Doesn't feel right, does it? It's not quite right. And yet we expect, even with this simple illustration, it shows that we really do approach the world differently. And we have things that are comfortable and perhaps things that are uncomfortable. And sometimes the way we have to use existing interfaces really is uncomfortable. Another thing we have to understand about humans is we basically enjoy having three-dimensional inputs, parallel information inputs. These are ones where we are combining information from not only our visual sense, but perhaps our audio sense. Indeed, we use sound to help reduce the ambiguity that we have visually and vice versa. We also generally work best with 3D motor control input. This is where instead of turning a steering wheel to drive our automobile, it would be much easier just to point in the direction we want to go. And we find that, of course, now the advent of touch screens on computer displays. Perhaps much easier to use a touch screen than to move a mouse around because we're more directly coupled. Some of the things that Ben mentioned about direct manipulation. And then finally, and this is a topic I'll discuss a little bit later, humans really build models. That's the way we interact with the world. We have all kinds of models in our head, and we call up these models depending upon the setting that we're in, and they help generate our expectations. We anticipate what will happen. In the case of a new program that we've loaded into our machine, perhaps there are some things we can anticipate in terms of a desktop metaphor, and there are things that we have to explore and discover. And as we do that, we build these models. Well, the next topic then is to look at the problems we see with current interfaces. Do we have a problem? Yes, we do. This next slide shows you that we have an overwhelming amount of information in the world. As a matter of fact, if you talk to educational philosophers, they will tell us that if we take the amount of information and knowledge that existed from the year 0 to the year 1800, by the year 1900, that amount of knowledge doubled. By the year 1950, it doubled again. By 1980, it doubled again. By 1995, it will double again. By the time we get to the millennium, we will have a doubling of the amount of knowledge and information that exists every 5 years or so. Well, how in the world are we going to keep up with it? Well, of course, some industries love to see this kind of situation, especially Weyerhaeuser and Georgia-Pacific and people that make newsprint. But a lot of people seem to think that we really aren't going to have a problem because we have the computer. And the computer is going to solve all of our problems. Well, the last time I logged into my email account at the University of Washington, a few months ago actually, a prompt came up on the screen that I had 833 new messages. So I decided I'm going to solve that problem. I'm just going to open several email accounts. I'll have an email account for my colleagues and one for my outside work and one for the various projects. And now I'll log on my email account and I have 30, 40, 50 messages on each of those. So are we really solving the problem? We have this marvelous way to distribute information. As a matter of fact, it's easier than Xeroxing because we can just create all these aliases and send these messages all over the world. Sometimes that's good, sometimes it's bad. Well, a lot of people think, well, since we have all of this information, what we need to do is sort of organize it better. So this is one way to organize information. The problem is, how are we going to access it? Indeed, this is the way we have been organizing libraries. We've been trying to put this knowledge into stacks so that we can then access those stacks. But really, we should be using the tools of our generation to help us make these advances, including the computer. But look at the problem that we have here. We have a tremendous intelligence inside this human and a growing intelligence inside that computing engine on the other side of the screen. But this is the way the two intelligences interact with each other, through a plate of glass through which we are placing highly coded symbols. And we're expecting this human to take those symbols, decode them, to try to add a semantics to it to understand what they mean, and then compare that with a model that they have in their own head, and then to interact with that machine through a keyboard that was developed many years ago, as you know, the QWERTY keyboard, that was actually laid out to slow us down. Because in the old days, the mechanical typewriters, the problem was that the keys were getting jammed. So therefore, the layout was placed in a way that would slow us down. But we have that same QWERTY keyboard hooked up to a machine that will perform 1 billion operations a second. So we have a problem, and the problem boils down to the interface. So basically, we can summarize some of these problems based upon our understanding of humans that indeed they do not represent the three-dimensional perceptual capabilities of the human. It really requires humans to be computer-like. We have to think the way the computer thinks generally. We have to understand the language of the computer in order to program. Generally, they're not intuitive, and one definition of intuitive means you pretty much know the next step to take. That once you have performed a number of prior sequences, generally it's sort of obvious what you do next. Furthermore, we're on the outside looking in. This means that we're sitting outside the computer terminal, and we're looking through this plate of glass into the mind of the computer. And all the computer knows is being sent through that little plate of glass, perhaps, and perhaps with some acoustic interfaces as well. So we are indeed on the outside looking in to the mind of the computer. And then we have this problem that there is very little interaction with the real world. We're either looking at the computer screen or trying to perform some task in the outside world, but we aren't able to put these two together to superimpose what the computer can add to the things that are going on in the real world simultaneously, superimposition. So all of these things add to the basic problem is that we have a limited bandwidth to the brain. And I should say actually between brains, between the brain of the computer, between and the human, as well as between humans through the computer. One of the best definitions that we can, or one of the best technologies I believe that we can use to solve this problem is what we call virtual interfaces. And let me give you a little anecdotal history about how virtual interfaces came to be. Many years ago, we were confronted with the problem of designing crew stations for advanced fighter cockpits. This, for example, is an F-16 aircraft. Depending upon the vintage of the aircraft, there may be up to 50 computers on board. Now, what this means is that this crew member, this single aviator, must interact in some way with those computers. In the case of the F-16 aircraft, for example, there's a computer for the digital fly-by-wire, for the air data, for the propulsion control, for the radar fire control system, for the stability augmentation system, and so forth. As a matter of fact, the aircraft really flies with computers. It sort of keeps it in the air. It's marginally stable, and we built it that way so it have high maneuverability. And as a matter of fact, if you ever have a power failure in the main bus of this aircraft, it just isn't going to be a good day. So the problem is, how in the world do humans interact with this very complex machine? Well, one of the ways this is, by the way, the way we do it now, with a conventional office that the pilot goes to. As you see in this particular photograph, this happens to be an F-18 aircraft. What we've done is taken all the information from those 50 or some odd computers, and now we've represented it not in one terminal, but several terminals around the cockpit. And what each of these terminals have done is taken a three-dimensional world, coded it, split it up into two-dimensional peepholes of a three-dimensional world placed around the cockpit. There is a vertical situation radar display here, a horizontal situation display here, stores management display here, and then through your head-up display, which projects virtual images, we see images at optical infinity that are what we call a vertical situation display. In a typical fighter cockpit, we may have 300 switches and 75 displays. And we have to operate this particular machine by ourselves, flying sometimes twice the speed of sound, trying to keep track of where the good guys are located and where the bad guys are located, pulling G's to the boundaries of consciousness and being shot at the same time. A friend of mine said it sounds like a standard day in New York City to him. Well, what we have to do now is really perform some kind of paradigm shift. The way we're doing things in the past just isn't cutting it, because again, this is not the way humans work. So what we started to do was to consider the use of virtual images and virtual worlds as a means of representing information. Now, a virtual image is something that you see or hear or touch that doesn't really exist. For example, when you got up this morning to go into the bathroom and looked at yourself in the mirror, what you saw on the other side of that glass was a virtual image of you. Not really you, but appeared to be you. Similarly, you could create acoustic images that appear to emanate from places in space, and tactile images which emanate from places in space, even though they're not really there, but they appear to be there. Now, in order to prove that this concept perhaps would work in a cockpit, we had to develop a number of technologies. And the concept was to build a virtual cockpit. And the virtual cockpit is basically a cockpit that the pilot wears. He would put on a magic helmet, put on a magic gloves, magic flight suit, and indeed with that be able to interact with his aircraft in a way he's never been able to before, using these natural capabilities, three-dimensional capabilities. Now, the way this virtual cockpit works is starting off with creating a very high-resolution picture on a miniature image source, such as this miniature cathode ray tube. This happens to be a half-inch cathode ray tube, and on this half-inch cathode ray tube we can scan it with 875 TV lines. Now, I don't know if you can see that very well, but that's a lot of picture elements on a half-inch tube. Now, on a 1-inch tube, we could scan it up with 1,200 TV lines. So that means in even your highest resolution computer displays, we could put that resolution on a 1-inch format cathode ray tube. And then the object was to magnify, collimate, and project this image so it appeared at optical infinity. And if we had two of these images, one going into each eye, we had the ability to create a stereo scene. So basically, it's like having an IMAX, stereo IMAX theater on your head. Panoramic scene at optical infinity, so it looks to be out in the distance. And then as you move your head around, this whole scene moves with your head. Now, with that same technology to generate the visual image, we also had to measure where that visual image was located. So we looked at a number of technologies for doing that. In 1969, we started working on a magnetic coupling, or an inductive coupling device, which is represented by this little magnetic cube that you see here. It's built by Palamas Navigation Sciences. This little cube contains 3 coils of wire wrapped around a ferrite material that is interrogated by another cube that's a little bit larger than this, contained in the cockpit, that sends out a mutating electromagnetic field that is picked up by this cube. And then when we picked up and transduced those fields, we can determine where this cube is located with 6 degrees of freedom relative to the radiating cube, with a precision up to 1 millimeter in translation and about 1/100th of a degree in rotation, 6 degrees of freedom, 3 in translation and 3 in rotation, up to maybe 500 to 1,000 times a second. Now, if we place this particular cube inside the headgear, when the crew member is looking around, we always know where he's looking and where the picture is located. So we can signal the computer when the crew member moves his head to the left to move the picture by the same amount to the right. And to do that rapidly so that as you scan out, move your head about, you in essence scroll out a virtual computer synthesized world. Now, the way we create a virtual acoustic world is by taking what we call an ear print. An ear print is basically a head-related transfer function. This is the way your ears process sound information. If you take the pinna cues of the ear, you can store that in a computer model, and then as coefficients in Fourier space. Then if you want to recreate a three-dimensional world from that, basically what you do is measure the instantaneous position of the head with this magnetic cube system, and then you determine which sound you want to display at what place in space, digitize that sound, and then you look up the coefficients from your ear print or your head-related transfer function, convolve it in the Fourier domain, then take your sound back out to the time domain, display it in a stereo headset, and lo and behold, you hear this sound in 3 space. As you move your head around, it stays in the same place. As a matter of fact, you can walk around this sound. You can reach out and grab it and move it and put it into another place. This way we can create a three-dimensional acoustic world, which goes along with our three-dimensional visual world. And then finally, what we have to have, of course, is a tactile world. And some of the forerunners of the so-called data glove helped us to do that. What we want to do, of course, is give the crew member an opportunity to interact with his virtual world using normal hand position, hand controls, and so forth. In this case, what we have is an instrumented glove. This happens to be a commercially available device called a data glove, but it's representative of the kind of computer input devices that recognize gestures from humans. In this particular device, we have fiber optics which link up to the fingers that allow us to measure actually the bending of each of the fingers independently, and we can signal that to the computer so that it knows basically the configuration of our hand at any point in time. And then we use the magnetic cube to measure the instantaneous orientation of the overall hand with 6 degrees of freedom. Now, if we also incorporate into this glove a vibrotactile array of stimulators or perhaps bladders, what we're able to do then is provide tactile feedback. For example, in the case of the virtual cockpit, we want to give this pilot an opportunity to activate switches that don't exist. The way you do that is move your hand into a particular region in a cockpit. And as your hand goes into that region, you feel it go over an edge, meaning you're into a control boundary or into a control volume. And when you're in that volume, the switch panel window's in. So you see the switch panel there. You reach out and touch it, you get the tactile feedback that you've touched that switch, you hear it click from that direction, you see that particular function light up, you take your hand away, the switch panel disappears, you don't need it anymore. As a matter of fact, it gets in the way. In many cases, we only use the switch panels in very limited portions of the mission. So there you have the idea of the virtual cockpit with the combination of visual, auditory, and tactile displays. Now, what kind of image would a pilot see? Well, this next scene represents what we call a mimetic display. A mimetic display is a display that represents the world, but it isn't exactly the world. It's sort of a cartoonish rendition of the world. But it basically captures the essence of what this crew member needs to see at any point in time. For example, we've taken a stored terrain database of information and overlaid it as a blanket over the real world. We've taken other aircraft, and we know their location, friendly aircraft up in the upper left, and you have another aircraft here that is circled by a yellow box, and that yellow box tells us that we don't know the identity of that aircraft. We also have a pathway in the sky where we'll fly automatically or manually that takes us around terrain obstacles, threat obstacles, and things like that. And then this whole scene moves by as sort of an optical flow that gives us a feeling for the altitude, attitude, and velocity of the aircraft without having to look at any instrument. Now, the power of this comes from the so-called gestalt. That means that we can look at this display and instantaneously determine where we stand. And we feel it is a powerful metaphor for displaying information to the pilot. Now, the main thing to think about is that this display contains the same information that we saw before. Let me substitute this quickly, and you see now the old display. Now, which one do you think you can remember? And which one do you think you can use effectively? We've known for years, since 1947, that we need to be drawing pictures for pilots. Paul Fitts, sort of the father and founder of human engineering, pretty much told us that. The problem was, at that time, we didn't have the technology to do it, but now we do. But there's more to the problem than just what we call the mimetic display or the inside-out display. We also have to have what we call the exocentric display, when we're on the outside looking into this overall world. In this case, we're showing a representation of a virtual fishbowl, or what we call a God's eye display, that would sit in the pilot's lap. And the object here is to have now a miniature world that is now basically a virtual world sitting in your lap. Now, you also have your inside-out view at the same time, remember? You're looking at this sphere of information that is presented as your mimetic display, but you also have this miniature sphere that gives you the other information. Now, the way you interact with this miniature sphere is you basically now use your virtual hand controller. For in this sphere, you have the miniature world, other data factors in there, or data points. And what you may want to do, for example, is interrogate one of these data points and ask a question. Where is that? And a simulated laser line comes out of your finger and goes into the outside world, and you see where that is in the outside world. Or you're looking at the outside world, and you say, where is that? And you see that line come back into your God's eye display. Now, we've never been able to do that before. This is a marvelous way to navigate in data space. It's also a marvelous way to navigate in real space. In all of these cases, what we've done is build virtual worlds that are see-through, that let us see the outside world and put information on top of it. to enhance our abilities to understand and maneuver and alter perhaps things in the real world. So now we can come back to the definition of virtual interfaces. We feel that virtual interfaces is a remarkable way of enhancing and extending our abilities and perhaps solving some of the problems we had before. Look at this particular definition of a virtual inclusive display. This is the way we do it now with a conventional display, as you see on your charts. This is the human, the black dot, and this is the display that the human is looking at, the empty circle. Now, this is the virtual display. Basically now the human is inside the machine. Now this can have remarkable meanings for us. Now, in order to prove that this whole concept would work, what we had to do was build a simulator. And one of the simulators that we built, we called our Darth Vader, our helmet. And you may have seen photographs of that. This is sort of a line drawing of that same system. The idea was to create now, with a set of optics and miniature cathode ray tubes like I showed you, a panoramic IMAX theater on your head that would be stabilized by this magnetic cube and would provide a way to interact with that world using speech, using eye control, and other kinds of interfaces. So we did indeed build these systems and try them out. And one of the remarkable things we discovered in 1977 when we started working on this virtual cockpit is that the promise of this technology could basically revolutionize the way that humans were interacting with machines. And in 1981, in September, when we turned this system on for the first time, it was like the beginning of a new world. It was like the same day that Alexander Graham Bell said to Mr. Watson over the telephone, "Mr. Watson, come quickly." It was unbelievable. Switching it on and having a panoramic display open up. The remarkable thing is it pulled you out of the seat that you were sitting in and sucked you into a computer-synthesized world. It took us many months to really discover what was happening. And it basically had to do with this inclusiveness. Many of the experiments we did after that pointed out that crew members would really able to learn very rapidly whole new ways of interacting with the world, like the mimetic display that I showed you before. In one experience, we brought in a number of crew members from Edwards Air Force Base to fly the virtual cockpit. And they were, of course, very skeptical to begin with, but after they had a chance to fly it, they decided that this was the only way to go. But the most exciting part of that particular experience was when I brought my daughters in, who were sophomore and junior in high school, and put them in the virtual cockpit, and they could do the same thing. Now, understand they couldn't solve all of the gaming problems. They didn't understand about radar signatures and infrared countermeasures and things like that. But what they could do is solve the geometry problems. So that pointed out to us that we had a whole new medium that could accelerate learning. One of the early things we did with sound was we had to create this is before the days of digital signal processing. We had to figure out a way to create three-dimensional sound. And the way we finally did that, and you'll have to excuse me, I'll turn this right side up here, as if you couldn't tell. This is a coffin-sized box in which we've taken a Keymar mannequin head mounted on a DC torquer. Well, actually two DC torquers, one that rotates the heads around the axis of the head, and then one that rotates the whole head this way. And then there's a speaker sitting on a rail that slides back and forth. You see a TV camera inside this so we can see what the head is doing. And this is a coffin-sized box. And what we'd basically do when the pilot's sitting in a cockpit moving his head around, we'd move this head around in the Keymar mannequin head with two microphones in the ears. And then we'd play the sound into the speaker and then listen to the sound come out through this Keymar mannequin head and display it into our cockpit headset. And sure enough, we could get 3D sound. Mind you, it was a very crude way to do it. And it only worked in a simulation because you wouldn't want to fly this thing in an airplane. But it allowed us to prove that this works. And then some of the other technologies we're working on, this happened to be one that we were test flying in 1973. This is what we call a model 7A display. And in this particular system, you have a little glare there, what we have is a symmetrical paraboloid, which is a visor, and a miniature cathode ray tube located in the back of the helmet. We send a signal over the top of the helmet. It projects into the visor, back into the central mirror, which is located here at the focal point of the paraboloid, back in the visor, and into the pilot's eyes. And then you could have two of these bouncing across the visor. This was in 1973. And it was actually being flight tested in several aircraft. This is one that we built in 1975. This is what we call the Model 8. And the Model 8 also has a projection into a parabolic visor, but we don't use the fiber optics bundle. This is a side view of the same display that you can see now, the cathode ray tube located here with the, a projection into a little patch that you see here, which is a trichroic coating that lets us basically see the outside world with this image presented at the same time. Other systems that were developed, this was one that was in the actual mid-80s, and this allowed us to basically take the head-up display that was normally in the aircraft and display it on the visor. Well, all of these systems have given us the confidence that indeed virtual interfaces will work. Now, this is perhaps one of the most important aspects of the virtual interface. What does it do in terms of the interacting with the models that we have in our head? Now, if we look at the way our conventional interfaces work, we have to realize that basically we're creating three models in our head, or we're using three models as we interact with the world. First of all, we have the model of the physical environment. Let's say that we're watching The Simpsons on television. Now, we're sitting in our living room watching the TV set with The Simpsons show. Now, we're sitting in this living room, which is our physical environment. We know where the television is located, where the bathroom and where the kitchen is located, and so forth, and we can navigate around in this world quite effectively. We also have our remote controller for our television set, and we know which buttons to push, hopefully, on our remote controller to change the volume and the channels and things like that. So the television is the medium which is within this physical environment. And then, of course, we have the message in that medium, which is The Simpsons show. Now, we've watched The Simpsons several times, and we know Bart Simpson's personality, and we can pretty much predict the way that, that he is going to perform in this particular show. Now, in watching the Bart Simpson show, we're basically using three models. We have the model of the message, Bart Simpson, we have the model of the medium that we're operating, and we have the model of the physical environment. Now look what happens when we go into a virtual environment. Here we have the human that has gone from watching the show in his living room, or her living room, moving inside the medium. So now we have a human inside this medium. The question is, what are the models that we have now? Where is the medium? Where is the message? And where is the environment? Well, what we find is that really the medium disappears. We don't see it as a medium anymore. What we see is, of course, the message. But the message becomes the same as the environment. So basically we're down to one model again, where our message and our environment are the same. Now, into that environment, we are carrying with us all the models that we built in our head throughout our childhood and our life. If we build that message really good, that means now that we have a tremendously high bandwidth in which we can link our model with the mind of the computer. So this leads us then to the potential advantages of virtual interfaces. First of all, we can say that it's experiential in that we're able to go into a place, hear and see and touch this place. Also, we have the ability to be immersed into any imaginable environment. Basically, it's whatever we program. This world is also transparent in that we can overlay it over the physical world, as you've seen before. It's intuitive in that we're now able to interact naturally using our natural abilities rather than trying to code our abilities and operate in the way the computer has to operate. Basically what we've done is make the computer Instead of making the human computer-like, we've made the computer human-like. And then this world and this environment is controllable. We can do some marvelous things that we cannot do in a physical environment. For example, like in Star Trek, we can beam ourselves around in this world. We can also manipulate time and space. We can scale ourselves to 1 millimeter high or to 10 feet high. We can change the law of gravity, Planck's constant, the speed of light, speed of sound, and so forth. What this finally results in is to high bandwidth to the brain. Now let's look a little more detail, in a little more detail to the virtual visual interface. If you look at your diagram, you can see now a very simplistic block diagram of a virtual visual interface. Basically, we're deriving state information from a network that goes into a graphics engine, which then goes into our end effectors. In the case of binocular display electronics, which may drive two image sources, one for the left eye and one for the right eye, of course. And then these images are relayed into the eyes through some kind of optical system. At the same time, within this headgear, we're measuring the instantaneous orientation and position of that headgear and playing that back to the computer, or this graphics engine, through a head tracking electronic system. So now we can basically scroll around within a virtual model, within a computer model of a virtual world. Now the way that we actually are able to interact with that display depends upon the way that we relay the images to the eye. Now this particular chart shows us the types of virtual visual displays. There are basically three types. There's a see-through type that we've seen before, where we're seeing the outside world with perhaps a virtual world superimpressed over the top of it. There's also the so-called occluded world, where we have a surrogate of the real world, which is represented only as computer images. So our normal vision to the outside world is occluded. And then we have finally the multiplex display. That means that by shifting our eye position, we go between the real world and the virtual world. But in this case, the virtual world is also collimated to optical infinity. So our reaccommodation to the display image is very easy if we're looking into the outside world. Now the next chart also shows the effect of some of these concepts. I mentioned to you before the see-through virtual display. Now in the see-through virtual display, what we have is a real-world image in which we're superimposing computer-generated images. In this case, the cursor and this pyramid that we see superimposed over the real world. And that is created by taking the image source and projecting it through a see-through combiner. That means we're able to see the outside world and the virtual image at the same time. The second kind of virtual world is the multiplex virtual world, where we're able to, again, see an unoccluded view of the real world. And by looking slightly downward, we're able to see now a virtual image that we can place at any distance. And this is achieved by taking an image source and projecting it into a special mirror, like a toroidal mirror, which actually collimates that scene to a particular distance. So we see an apparent virtual image, and this gives us an easy way to switch between the real world view and the virtual world view. And then finally, the inclusive virtual display. This is where we're looking at only the occluded image. In this case, we're showing a subject who is actually interacting with molecules and manipulating molecules by taking a virtual hand controller, in this case we call it a wand, and grabbing molecules or atoms and moving them around to create new compounds. Again, this person is able to move around in that world, able to interact with those molecules as if they're scaled to the size of the computer-generated molecules. Now the applications of virtual worlds are many. And they sort of go to the far reaches of your imagination. And I have actually given you in your handouts a number of applications that we've thought of, but the applications come from the ways that we hook these three types of virtual visual interfaces, and acoustic interfaces, and tactile interfaces with computer models. This chart of the categories of virtual worlds shows some of these things. It depends upon whether we're taking a scanned model of the real world and looking at it, or synthesizing a model as an architect would do so, or we're working in a metaphor space, such as representing some of the types of information that Ben had showed you earlier, the New York Stock Exchange, perhaps mortgage data and things like that. But perhaps one of the most exciting aspects of this technology is what we call real-time telepresence. And this is where we're able to put our eyes and our ears and our hands into another place, perhaps through a broadband telecommunications network, so that we could be having this conference virtually, that we could indeed be sitting in the same virtual place, or what we call a virtual common, and interacting with each other, indeed being able to reach out and touch someone and get the tactile feedback that they are there, along with their representations. What I'd like to do next is to show you a short clip of a model of virtual Seattle that was built by using just a limited number of polygons. Now, in this particular simulation, what we're doing is taking the data glove that you see here, using the fiber optics Ascent's finger position, and the so-called iPhones manufactured by BPO Research, used to represent the binocular visual world. Now, as we put our headset on, basically we go from the physical world standing into the virtual world. And this virtual world happens to be this model of virtual Seattle. Now, we start off looking out on Elliott Bay in Puget Sound. We see the Olympic Mountain Range. We see also a whirlpool in the middle of Puget Sound. Now, we can put these kind of things into our worlds that you can't put in the real world. Also, looking now to the right, you see Mount Rainier in the distance and the skyline of Seattle with the Keene Dome on the right and the Space Needle up at the end. And there's a ferry going back and forth to Winslow from the dockside in Seattle. We're going to fly over the Keene Dome here, and you see Meredith wearing the headset, and as she moves her head around, we're scanning out this image in real time. And she's pointing her hand, and as she points her hand and makes a gesture to the computer, she's able to fly within this model. Then as she flies down to the Space Needle and puts her ear toward the Space Needle, she hears the people in the restaurant clinking their glasses in the top of the Space Needle. Now she's just flying through the Boeing cloud. That's where most of the Boeing airplanes exist. Now we see an orca swimming by, and if we want to hitchhike a ride on the back of the orca, we make a hitchhiking signal, a gesture to our computer, and now we're riding along with a calf beside the mother orca. Or we can jump into the ferry and fly the ferry back, or ride the ferry back and forth. This is really a marvelously wonderful thing. You remember the dreams that you have about flying? Well, now you can really do it. If you make a rock gesture, you actually descend through that whirlpool to underwater Seattle, where you can play tag with an octopus. And there's a buried treasure there, too. You can hook up that with that buried treasure. Now, Meredith just flew through one of the portals into what we call our Green Valley. When you fly through Rainier, you get to the Green Valley. And the Green Valley is a magic place. Meredith just picked up an egg and let it drop, and it broke open. And now what we call an autonomous entity emerged from this. Now, autonomous entity is an object that has intelligence. This is actually a virtual bird. Now, in this case, we're holding out our disembodied hand and an open palm gesture. And the bird recognizes that as a friendly gesture and will come now and land on our hands. And you have to understand that we also can talk to the animals, just like Dr. Dolittle. And this particular world, by the way, we created to help children understand about ecology, kindergarten and first graders. In this world also you can become a tree or a bird or a frog and send these birds out to build their nests and so forth. Here comes the bird. We're bringing it up close to us. And although it doesn't exist now, we're working on the technology eventually to be able to feel the bird as it lands on our hand. So if we want to become a frog, here goes a frog jumping by. We can actually go inside and inhabit that frog. We can map our virtual body into the body of the frog and jump around into this field and looking through the frog's eyes. And now as we begin to fly back through the backside, the south side of Mount Rainier, we hear the waterfall on the right-hand side as we move by. Again, all of the entities in virtual worlds have attributes of sound, of reflectivity, of elasticity, and we can map humans into those worlds. Now, as we fly through the backside of Mount Rainier, we're ported back into virtual Seattle. Now, in this particular model of virtual Seattle, we're only one person interacting with the computer model. But in future virtual worlds, we hope to have several people that are participating together. And even though these models that you see are very simplistic, it's amazing how realistic they seem to be. When you walk along the street in Seattle up to the base of the Space Needle and look up, it's like you're really there. William James back in 1890 said, part of what we perceive comes from the object in front of us. The other part always comes out of our own head. And that's part of the power of virtual interfaces, that we're bringing as much to the world as the world brings to us. Now, we've learned many things from our experiences. Let me show you a few more, actually. I'm getting a little bit sidetracked here. My time is running out, and I believe we've unplugged the projector here, Ben, but perhaps you can still see this. Yes. This is a commercial product. It will be introduced at the Consumer Electronics Show in Las Vegas coming up in January. This is the very first commercial product that is what we called a metaphor space, or I'm sorry, not a metaphor space, but the multiplex virtual worlds. And in this particular device, what we have is a module in which we can either tune in commercial television, or we can actually link it to a transmitter that's located somewhere in our house. For example, if we want to take our camcorder, put our camcorder looking at our baby in a crib, we can then data link that, transmit it to our receiver, which is located on our hip. And then when we put on our magic glasses, we see the outside world completely unoccluded, but we look downward and we see this monitor picture of our child. Or if we're at a football game, we want to watch the football game, and it's unfortunate when you go to the real football game, you don't get the instant replays. Well, in this case, what you do is you wear your television set. So you watch the football game, and then when the play is over, you just glance down a little bit, and now you see the replay in your virtual vision eyeglasses. Another thing that we've learned is how to... I need to turn this on, actually. Okay. There we go. All right. Sorry for the delay. One of the other applications of this is to be able to go into wear them so that we can go jogging. And if we just wear a special device, a pulse Doppler radar around our waist, also incorporated in this module, we're able to tell the speed at which we're running. And then we put a little sensor up here at our temple and measures our pulse rate. So now what we have is a combination of how fast we're running and our pulse rate to go that fast. So we basically have a built-in stress tester that displays to us the instantaneous caloric burn rate, our particular stress level, and so forth. If we're a firefighter and we're trying to go into a building, we're able now to map ourselves inside that building and know where we're located, where the other firefighters are located. We can look at a door, and as we look at that door, we get a representation of the information that has to do with the particular temperature of that door and perhaps the concentration of noxic gases within the room where we're located. Now, in our experiences in using these virtual worlds, we have gleaned that it's very important to create a wide field of view presentation. Indeed, it takes about 60 to 80 degrees to create this immersion effect. And immersion is important in order to make this model switch from being on the outside looking in to being on the inside. Field of view is important, and that's why IMAX theaters or OmniMax, Omnidome theaters work so well. That once you are indeed immersed, then you're able to create models very rapidly and change the models that you already have. We find that even limited polygon worlds work very well, and that children can build these worlds quite effectively. We've had experience now with 100 children who have come into virtual worlds and created their own worlds quite handily without being computer literate. And then finally, one of the things that happens when you in an immersed experience is you never forget it. Once you've been in a virtual world, you never forget it. It's like going to Disney World, and it becomes that kind of thing. Now, there are a number of issues associated with developing virtual worlds, one of which I want to mention has to do with the problem of how in the world do we create a high-definition picture. For years we've been concerned about this. In order to use the existing technology where we're creating aerial images, then we have a situation where we basically are taking a large picture or a miniature picture and magnifying it to a large picture and looking at it through very large optics to see this wide field of view presentation. The problem with this type of approach is it becomes very kludgy, the optics become very heavy and bothersome. Well, at the University of Washington, we're pioneering a whole new concept we call a virtual retinal display. In the virtual retinal display, basically what we're doing is scanning an image directly on the retina of the eye. We're creating a photon generator that creates a stream of photons which are modulated with video signals, and then are scanned such that the screen on which they project is the retina of the eye. There is no intermediate image plane anywhere. That means that we can now create the projector, which is very small, on the order of half an inch by 1 inch by a quarter inch thick, that projects onto a toroidal combiner, able to create a panoramic scene up to 120 degrees, 60 degrees, with a resolution of 4,000 by 3,000 picture elements going into each eye. Now we're talking about photographic quality. Now, but we're also creating another problem of how in the world do we get the graphics engines to create an image that has that kind of resolution. That indeed is one of the other challenges. Well, let me now skip to perhaps the final piece of this, is what is really going on in VR today. The media, of course, has been replete with information about VR. A lot of speculation and extrapolation of where this is going. I've been working on it for 26 years, so it isn't really anything that's brand new. It's been around for a long time, and just like every other technology, things really do evolve. But it has been, a lot of extrapolations have taken us into areas where we don't necessarily believe are effective ways to use the technology. We see also some of the first exposures to the public of this technology being in games of violence. When we allowed those 100 kids to build their own worlds, there was not one bit of violence in it. As a matter of fact, these worlds were peaceful worlds. They were worlds where they were beautiful. And we have to understand that generally the people that generate games are adults. The systems now are very expensive. And one of the things that we're trying to do, along with other laboratories around the country, is bring the cost down, because that's what will make it practical and usable, not only in businesses and industry, but in classrooms. And hopefully, in the future, sitting down at your PC at home or at work, you will be wearing your computer rather than looking at a screen. Thank you very much for your attention.
Welcome to the fourth hour of User Interface Strategies 93. We've begun to receive several faxed-in questions from audiences around the country, and we'd like to encourage you to keep sending those questions in. We'll be getting to them during the fifth hour. The fourth hour will be a virtual James Martin, who will present his lecture by videotape as prearranged. James Martin is one of the leaders in the data processing and business information communities. He's written more than 80 books on various topics of networks, database, telecommunications, and one of the books was nominated for a Pulitzer Prize called The Wireless Society. I admire him for his capacity to integrate concepts in a remarkable way and give me a vision of the future that I didn't anticipate. In this segment, he'll give us a new concept of what user interfaces are all about. For most of us, we think of a user interface as something that we use to operate a computer. For James Martin, user interface is something to operate a company or a larger world itself. And that user interface design question that he's dealing with is how to design an environment to represent the operations of a corporation or a large organization so that a manager can make effective decisions and put them into play. Here's James Martin.
Hello, everybody out there in satellite land. Our world is becoming very complex. Corporations are getting much more complex, partly because of computers and networks and information technology and globalization. Now, it's becoming very important as corporations become complex to be able to design them. And so what we're going to talk about for the next 55 minutes is how you can visualize complexity, how you can visualize complex enterprises, what sort of tools we need for doing that. And when we talk about visualizing enterprises, we really want the business people to be able to do the modeling of the enterprise and do the visualization. So what are the best techniques with which we can visualize complexity? Now, over the last few years, we've seen the computer industry evolve CASE tools, computer-aided systems engineering tools. And these tools give us the capability to build models of things which are extremely complex and build them with enough precision that we can generate code from the CASE tools. So I'd like to start by illustrating CASE tools and how they have evolved to let us visualize complexity, and then go on from that to say we need much more than tools for programmers now. We need tools for redesigning the business. And furthermore, we need tools which are not just understood by programmers or technical people, but tools which can help business people to redesign their business. Now, probably the best type of technique for helping us to visualize great complexity is object-oriented, the object-oriented view of the world. And so I'd like to talk about why I think that is true, why object-oriented is so important. Now, many people, when they think about object-oriented, think about object-oriented languages and object-oriented programming. But really, if we're going to visualize a complex world in an object-oriented fashion, then we want object-oriented modeling and object-oriented analysis. And I believe that's going to be the key to visualizing very complex corporations so that we can redesign them. Now, we need to be able to represent the activities and the flow of work in a corporation. And when we build models of the flow of work, we need to be able to say what rules constrain that. Events happen. When events happen, there are certain business policies which determine what you do about those events. So I'd like to talk about event diagrams and rules and how we can build models with rules which are object-oriented models. Now, what we would really like to be able to do is to create models which enable us to visualize the enterprise in such a way that we can execute those models. We'd like to be able to simulate the enterprise and then look at lots of alternate redesigns. So we really want to build executable models of an enterprise. And that raises an interesting question. What sort of models are likely to be executable, but also are models which the business people can understand so that they can participate with IT professionals in the redesign of a business? And as we get to the end of the 90s, I think we're going to get to a stage in which we want to be able to implement code. We want to be able to generate code with CASE tools and generate code which directly relates to the business visualization and the business modeling, so that when business people change their policies, you can immediately and automatically translate from the proposed change in policy into the simulation of the business and then the generation of code for running the business. So very important, very exciting set of topics. Now, there's no corporation that doesn't need to be redesigned today. And they need to be redesigned because of technology, because of networks, because of globalization. But also they need to be redesigned because we've let lots of bureaucracy grow up and let lots of redundancy. And where we do not have the capability to visualize and model complexity, business people cannot see that redundancy. And what we're finding is now that we're beginning to get techniques which enable us to model very complex situations, those techniques are revealing to us that there is an enormous amount of need to fundamentally redesign our processes, redesign our businesses. Now, this is a very complex subject, and we cannot go into all of the detail that would teach it to people. But what I'd like to do during the next 50 minutes is to show you segments, to use segments from courses which I've made with James Martin Insight on the subject. And so we're going to be cutting into tapes which go into a lot more depth than we have time to go into in 50 minutes or so. And first I'd like to introduce Peter Keene, who has written some great books on the subject of business redesign, and he's a great authority on how telecommunications enables you to fundamentally change the speed at which you can get information, and hence the speed at which we make business decisions.
Applying just to get a certified document in Ontario, for example. It's a classic example of how you change everything just through the availability of that technology. The registrar's office there has birth certificates, divorce certificates, marriage, whatever. And I think there's something like 40 million of them. They're bound in books, each weighing 40 pounds. So in fact, disabled work people can't work there. Typically it takes about 3 days to find a document. I mean, all the processes we know. I shouldn't say, but that's absurd. It makes no sense whatsoever. But we have no choice. Documents are there because of location dependence. Now, you scan it, it assigns a number, stored on a jukebox, a database, cross-links. In that case, we're talking about being able to get any certified document in minutes. The work's more interesting. As in the case of radiology, two people can look at the same document, a doctor looking at a medical record here, the insurer looking at it here. And this, I think, is an illustration of how the technologies that have most impact can sort of sneak up on us. And it's when the tool becomes available and the creative thinking is there, wham. In fact, I often call them wham technologies.
Those illustrations from Peter Keene illustrate what a dramatic shrinkage in time can happen by using today's technology appropriately. But in order to do that, we have got to redesign some very complex business processes. And in order to do that redesign, we'd like to have computerized tools to help. Now, the computerized tools can have diagrams of the business processes rather like case tools. CASE has really introduced an engineering-like discipline into the creation of software and systems. We can look back all the way through history and we can observe engineers having to draw things, and they need to have disciplined ways of drawing complex things which enable engineers to visualize in great detail what they have drawn. And this discipline has now come into the programming world. I think one of my favorite illustrations, which I used in a course on case technology, shows engineering drawings of a bridge in Chicago, and these drawings are 90 years old. The evolution of case is the coming of an engineering discipline to software development. And just like other engineers, we want to be able to draw diagrams which have standards and which are extremely precise. For example, here's a diagram which was drawn at the turn of a century, and this is what mechanical engineers have to draw. And this shows a great amount of detail. Here we've got a huge gear, massive gear, and this is a diagram for a bridge in Chicago. Here's the worm, and this is the mechanism which opens the bridge and raises it. Now, really from the beginning of engineering, engineers have had to draw diagrams like this. Now, can you imagine them trying to create that bridge? I go by this bridge every day in Chicago. Can you imagine trying to build a bridge that's going to work? This thing's worked for 90 years now, if they weren't able to draw diagrams of it. Now, we've been trying to build things much more complex than this bridge. The corporate software is many orders of magnitude more complex than this bridge, and we've been trying to create that without engineering like diagrams. It's not surprising that software has been a mess. And so the coming of CASE is the coming of an engineering discipline in which we want to be able to create exceedingly precise diagrams to represent an enterprise and to translate that enterprise into the software which makes the enterprise work as effectively as possible. With case tools, we create diagrams, and the diagrams have got to have an engineering-like precision because they've got to lead to code generation. And what case is really all about is raising the level of abstraction, which means getting higher level ways of visualizing the system that we want to build and visualizing it with enough precision that we can drive a code generator. And we'd really like to take that now to a higher level of abstraction where we can visualize the business and express what the business policies are and then drive down from that into code generation. So in the history of the evolution of case tools, we've been asking the question, what are the best types of diagrams for helping us to visualize systems that we want to build?
In this window, in the upper left, I have my context diagram. I've zoomed it a little bit smaller so we can see it better. And in this window, I have my system diagram, which will also zoom smaller so we can see it better. And I'll center it a little. And we can, at the same time, see what we're working on in two different places. If I choose to change my system diagram, I could make it bigger and work on it like this.
The diagrams we use with case tools are a language, a high-level language, but it's got also to be a very precise language with there's rich semantics associated with the diagram. Now, the meaning of the diagrams has to be stored in a repository. So the heart of case tools is a repository. And the repository becomes very complex because it's got to store a lot of meaning which we communicate to the repository by manipulating the diagrams. There are many different types of information which we really want to store in that meta model. You want to store information for planning, and you want to store the stuff of the data administrator, all of the entity types and relationships and attributes, the normalized data. And you want to store the information which is interesting for the redesign of a corporation. So lots of objects on here which relate to high-level analysis, business process redesign, and so on. And then we want to drive down from those to the detailed design, and so information which relates to the detailed data flow diagrams, action diagrams, the screens, the painting of GUI interfaces. And then we want to store the code, so code generation. And we also want to store planning information for the management, metrics and management. So there's a great diversity of information which we store in this meta model. Today we're discovering, as we start to visualize enterprises, that there's a desperate need to redesign most corporations. In fact, as we look back at the last 10 years, we'd say we've spent an awful lot of money on computers and information technology, but most of the time we have been building the wrong system, because what we ought to have been able to do was to visualize the enterprise and redesign it, and then build a system for the redesign. Now, one corporation, one giant corporation, one of the biggest corporations in the world that's been doing a lot of business redesign is General Electric. And an executive in General Electric who has been a catalyst in making that happen is a wonderful guy, Don McNamara, very fascinating person. And he's very much concerned with the fact that it's important to look at the business before you spend a lot of money on building IT systems.
It is important to have a clear, very clear concept of the direction, the vision, and the mission, and the direction of the corporation, as well as the goals and objectives of the process that's being addressed, before you do a system requirements or a system design session. And we often spend more time designing the business process, getting the vision straight and the goals straight, than we do designing the information system. And we do that because we've learned the hard way that if we don't, we're just going to build the wrong system to meet the wrong objectives.
In order to do business redesign, we need to create a model of the activities which are going on in an enterprise. Now, the activities are so complex that nobody understands all of them. The person at the top has got an inappropriate idea of what's going on at the bottom, and the people at the bottom don't understand what's going on in other parts of the enterprise. So therefore, we want a model of the activities. We want to model it and then understand the model. Then when we understand it, redesign it, probably do multiple redesigns, and then simulate the effects of the redesign. Now, in order to get this visualization of the enterprise correct, we need to have the business people thoroughly involved in the business modeling. In fact, probably the business modeling ought to take place at two levels. At the first level, let's call it level one. Level one should probably be done by the business people themselves. So the business people are creating a model with the IT organization guiding them in how to do it. And then the second level, we take that model and we add enough detail and enough precision to it that we can generate code from the business model. Now, one bank in Canada, the Canadian Imperial Commerce Bank, has had the business people, not IT people, the business people modeling the activities in the bank, and as a result of that has been able to introduce major redesigns, major improvements in efficiency of the banking operations.
Well, back in 1990, the Chief Information Officer, who is also the Executive Vice President of Information Technology Division, requested a small team headed by myself to look into the flow charting, looking at the processes that the branch performs, because it was felt that there's a need to improve these processes and to make them more cost effective. And as a result of that, we looked at a number of methodologies that are available, and we came to the conclusion, after looking at a few as well as some computerized tools, to select IDEF. Then we had a consulting firm from Boston for a period of 5 or 6 days teach us the IDEF methodology. And, you know, we took it from there. We selected one particular process to validate our selection. And this is the clearing process, whereby if you walk into a branch and make a deposit, what happens at the cashier or teller, what does he or she perform? At the same time, we would then flowchart the activities, other activities within the branch. What our experience has been when we flowcharted the clearing exercise, we balanced that check 16 different times. And, you know, obviously that's far too many, and so there must be opportunities to simplify that balancing operation, if nothing else. Well, the number of diagrams that are involved were approximately 35. And they would have, on each diagram, you would have maybe 4 or 5 boxes which would describe the activity that was involved. And, but the IDEF methodology, how it works is that that the modeler will interview the business expert. So if you are, let's say, a teller, we will come to you and say, well, what in fact do you do to handle this particular transaction? We take down this information on a piece of paper, go to the terminal, to the PC, and draw the boxes and the activities that you have described to us. Now, what we do then is we feed that back to you and say, well, we give the diagrams to you and say, well, this is what you have told us. Is this correct? And you may say, well, John, well, that's not entirely what I left some steps out, and these are the corrections that you should make. You feed that back to us, and then the modeler will make those changes, feed it back to you once more, and you say, you got it correct this time, and then we go on to the next level. Because what happens in the IDEF methodology, you start with a high-level project, and you say, well, processing clearing, that may be the high-level box. And then you decompose it, what happens at the branch level, what happens at the data center level, what has happened by the teller, what happened by the other people in the back office. So as you decompose it, you verify with the business expert exactly what they have told you and what you have flowcharted. So their involvement is constant, and I think that is, very, very important, and that it is in fact their model, not the modeler's model. It's the business people's model, and they take ownership of that, and they in fact identify the re-engineering opportunities.
The interesting thing in what John Bumister is describing there is that it was the business people that did the business modeling. Now, that's what you'd like. You'd like the business people to be able to model and redesign their own business. Now, as soon as we create these models of complex situations, we discover that there are just the most amazing inefficiencies going on. In that bank, they discovered that there were some checks which were being balanced 16 times because the branch didn't know what the district was doing and the district didn't know what the computer organization was doing. And this is common. Every time we do detailed business modeling, we find that there's no end of scope for improving, getting rid of redundancies, doing things in a much better way. We find that many of the activities which are going on do not add value substantially, so we want to be able to redesign the processes. Peter Keene tells a story about one of the largest stockbrokers in New York, and their auditors discovered that in their Federal Express bill, a very large proportion of that was documents which were going from Manhattan to Manhattan via Federal Express, which meant they were being flown all the way to Memphis and then flown all the way back again. In fact, even worse than that, many of the documents were going from the 2nd floor to the 17th floor via Memphis. And our industry is absolutely full of things like that, so we would like to be able to model processes and then streamline and make the businesses as efficient as possible. Now, probably one of the best ways to model very complex situations is with object-oriented techniques. And I think the whole of computing is going to become object-oriented. When we are a baby and we come into existence, we learn about objects. We discover that objects have certain types of behavior. So we might discover that there are such things as containers, for example, and containers can fit into containers. And sometimes objects can communicate with other objects, like the thing which controls the television. We discover that objects have certain functions. If you put a pair of binoculars to your ears instead of your eyes, they don't really do very much good. Now, one might compare the way the babies that we're looking at here are learning about the world with the way bankers can learn about the world when they think about their bank in terms of objects and the way objects behave. And we want to be able to have diagram types which represent the way that objects behave. And then we'd like to be able to draw diagrams which show activities and events. When events happen, they cause you to do something to an object. And when an event happens, there are certain business policies which affect what you would do to the objects. So object-oriented modeling, then, I believe, is a very valuable approach to the subject of visualizing complex enterprises and redesigning them. Increasingly today, we're building software which spans different machines. We talk about cooperative processing and client-server systems, and usually the best way to build that type of software is with objects, where an object on one machine sends requests to an object on a different machine, and the object on the different machine responds. And so we're likely to get a very complex world of software in which you've got networks and software on many different computers interacting with software on other computers. The network becomes rather like the nervous system of a corporation. And so we have a nervous system then which interconnects many different objects, all of which do their own thing. Now that tends to suggest a biological analogy to software. And David Taylor particularly emphasizes that the way we think about software today is remarkably like the way nature has built things.
Nature obviously has done a phenomenal job, if you will, of building very complex systems, if you look around at the incredible variety of living things. And as I look at nature, I see three key mechanisms that help to manage that complexity. The first one is that there's one kind of building block in all of nature.
The cells of nature, the cells of which your body is built up, are exceedingly complex. It would be unthinkable to go inside one of the cells and interfere with it, interfere with its DNA or interfere with its protein molecules. And so therefore the way nature works is that you have encapsulation. You cannot interfere with what's inside the cell. Instead you send messages to the cells, chemical messages or electrical messages.
The cell is basically a capsule containing related behavior and information. The information is captured in the RNA and the DNA, and the behavior has to do with protein conversion and some of the other processes that have to happen within a living cell. But the important thing is those are all hidden within the cell membrane, so that it's no one else's business in the outside world how that cell functions. It's a self-contained unit. The second level or key mechanism is that cells interact through a rather disciplined series of messages. Typically, they're chemical messages. In the case of the nervous system, they're a combination of electrochemical messages. But the important thing is if one cell wants to get another cell to do something, it doesn't go mess with its RNA or its DNA. It sends it a message that says, can you perform this service for me?
Our world is exceedingly complex, and so therefore we categorize it. We think of high-level objects and divide those into types of that object, and divide those into types of that object, and so on. And this is the way that biologists think about nature. There are cells, and then you have types of cells, like blood cells and brain cells, and different types of blood cells. So nature seems to have categorized the cells. It has a hierarchy of cells in a similar way to the way that we build a hierarchy of classes in software.
And the third level is that if you look at the cells, they're not just one kind of cell, but there's a virtually infinite variety of cells. And each of them is increasingly specialized. If you look carefully at how these cells relate to one another, you see that they fall into a relatively neat hierarchy. That hierarchy didn't arise to make biologists' jobs easier. It arose out of increasing specialization over the course of evolution. But the interesting thing about that hierarchy is that all the cells that are low down in it, like a striate muscle cell, partake of all the higher levels, a generic muscle cell and up to a cell in general. So that what we see is increasing specialization without the redundancy of information.
There are certain very important principles that we're talking about here. We divide software up into objects, and objects have encapsulation, as we were illustrating on these diagrams. The object contains data and methods, and they're encapsulated, and you can't go inside and interfere with the data. The only thing you can do is send a request for the object to execute its methods. So objects and encapsulation are a very important idea. They communicate by means of messages in which one object sends a request to other objects. And we have many different types of objects, so we classify them with a hierarchy, and the high-level object has subtypes which inherit the methods of the parent, and they have subtypes which inherit their methods, and so on. And so we end up with a tree, a classification tree of the objects that we use in software. Now that seems to be, once again, very much like what happens in nature.
Basically, the object is analogous to the cell. It is a self-contained unit that encapsulates its own information and its procedures. The chemical messages between cells are exactly like the messages that travel between objects, and they have the same benefits. They allow the cell to hide its information and protect itself and hide its complexity as well. So we have good modularization from objects. And a third key mechanism, the notion of a classification hierarchy, is exactly analogous to the classification hierarchy that we have of different kinds of classes, different kinds of objects.
One more basic principle: objects are built out of other objects. So we built objects out of objects out of objects, and that enables us to have very complex objects where, once again, you don't go inside the object and interfere with it. You merely send messages to it so that it can behave in its particular way. And again, that seems to be like nature. The retina in your eye is built out of cells. Your eye has got many components, including the retina. The eye is one particular object. So we have various objects which compose your body and, in fact, compose the whole of nature.
There's another way in which actually we can learn something from nature and apply it to software systems as well. And that is that if you look at the human body, it's not an undifferentiated mass of cells. It's not just chaos in there. But in fact, the cells are organized at the first level into what we call, interestingly enough, organs, like the heart and the lung and the brain. And above that level, there's another level of organization. Organs are organized into systems, the circulatory system, the nervous system. And then finally, those systems are organized into an organism. Notice that word coming up, that root word coming up over and over again. And the beauty of this kind of organization is that it simplifies both the construction and the understanding of these complex systems. For example, you can examine the heart and you can look at it purely as a pump. Fluid comes in, it goes through valves, fluid goes out, and you don't have to worry about how a striate or smooth muscle cell knows how to contract and elongate along its longitudinal axis. You just don't have to worry about that low-level stuff. And if you look at how the organs interact in the body, they tend to interact through high-level messages among the different organs and not mess with each other's internal details. So here we see nature not only modularizing at the lowest level in cells, but also doing what I call multi-level modularization. So we're modularizing at the organ, and then we're modularizing again at the system, and then we're modularizing at the whole individual. And if you like, you can go beyond that and say we're modularizing individuals who work together collectively in ecologies. So we see in nature a very multi-level modularization process that brings order out of chaos.
Now we can describe what are objects and subtyping of objects and encapsulation of objects and so on. But we also want to describe how the objects behave. So we're concerned with activities. There are a whole sequence of activities when you're running a corporation. And events happen. And when an event happens, that changes the state of an object. And the event triggers certain other types of activities. And so therefore we can draw a diagram which is just a workflow diagram which only shows activities. Or we can drop that into a bit more detail. We can have a diagram which shows activities and events, where the events are little triangles and the events change the state of an object. And with an event diagram, we can really model any types of events. You know, I've always wanted an excuse for putting a car chase into one of the tutorial tapes I do. I love car chases in the movies. And how about this for an excuse for a car chase? Now, you could take almost any situation and describe it in terms of objects and events. Take a scenario, for example, where there's somebody coming up to a traffic light. The traffic light changes to red, and the driver may or may not stop. Let's suppose the driver decides not to stop. He runs the red light, and a police car sees him. The police car may decide to chase him, or they may not chase him. If they chase him, then a whole set of events happen. Now, we could describe that with our object-oriented language. There are certain objects. We have the police car, we have the traffic light, we have the driver, we have the chase. The police car's got a siren, and he might switch his siren on. He's got a light on top of his car, and he might switch that on. And there's a ticket. He might give the driver a ticket. Now, we can draw an object relationship diagram showing all of those objects and the relationships among the objects. And on this diagram, we want to represent the cardinalities. So, for example, the police observe the traffic light. The traffic light is ignored by drivers, so we have cardinality symbols on the diagram. Now we want to be able to express the events which occur. First event, there's a clock tick which causes the traffic lights to change color. This is the event traffic light changing. We can subtype that event. The traffic light might change to green, or it might change to red. Then there's the moving driver, which is coming up to the traffic light, and he's got to decide, do I stop or not? So here, is the driver reacting? So this is the event in which the driver is looking at the traffic light, and he's got to decide now, do I stop or do I run the red light? Well, let's suppose he runs the red light. That's this subtype of the event. And so then the police see him. So now here's the block where the police are deciding what to do. And so this is the event, which is the police action decided, and this is subtyped. The police might not see the infraction, or the police might decide to ignore it, or the police might decide to chase him and give him a ticket. Well, it's much better television if the police decide to chase him. So let's suppose that this is the subtype here. Now the police activate the siren and lights on top of the police car, and they chase after this driver. Now the driver looks in his rearview mirror, and he sees the police car coming after him. And he's got to decide now, what does he do? So this event is also subtyped. He might decide that he's going to outrun the police. He's going to put his foot hard on the accelerator and try and get away from them. Or he might decide he's going to stop. If he stops, then the police issue a ticket. On the other hand, if he tries to evade the chasing car, then we get a car chase, and two events might result from that. So again, this event is subtyped. One subtype is that the driver gets away, in which case we've lost him, and that's the end of the story. The other subtype is that the driver gets caught, and if the driver gets caught, then the police are going to stop him and issue a ticket. It's not as good as the car chase in Bullet, is it, or Lethal Weapon 3. But the point is that any set of activities like that you can model with an event diagram where the events change the state of objects. Now you want to be able to connect a diagram like that to an expression of the rules in a business. So in a business we have a whole lot of activities, we model the activities, say what the events are, and then we want to say, now what are the business rules? What are the business policies? And we want to be able to express those business policies. Incidentally, some people talk about rules just to mean the cardinality rules on an entity relationship diagram. And that doesn't represent business rules at all. Business rules are really the policies of the business people and deciding how they deal with the situations of the business. Now, we'd like to be able to represent those policies in English, but we'd like to do that in such a way that the English is very precise. And so we'd like a case tool which enables us to build the English representation of the business rules and at the same time generate code as it does that, so that you can then simulate the activities and the business events which are happening. Here we're looking at an event diagram on the screen of a case tool, the relatively new object management workbench from IntelliCorp. Now this case tool gives us the capability to not only create event diagrams, but to link the events and the triggers and the objects to rules. And we express the rules in English. We, at the same time that we build the rule with the rule editor, generate code, and that then enables us to instantiate the rules. Now the best way probably for business people to be able to understand that and to visualize it is with spreadsheets. They're used to spreadsheets. So when they think about their business, we would like to be able to generate spreadsheets, and from spreadsheets we can generate all the charts, the bar charts and the pie charts and the other charts which we use with spreadsheets. So one of the things we'd like with the business modeling tools is to be able to express a model of the business, and then from that generate spreadsheets and use those spreadsheets then for simulating the effects of possible redesigns of the business. And so what we're looking at here is, again, the IntelliCorp object management workbench, where you are seeing animation of the diagram with the various blocks lighting up as you go through a sequence of events and activities. Where we model a set of activities in a business, we would like to ask the question for each activity, does it add value? How much value does it add? And so there's a new type of costing which has grown up relatively recently, which is called activity-based costing. And this is allocating costs to the activities in an enterprise. But that just describes costs, and it doesn't describe the net added value. So one would like to go further than activity-based costing and say with each activity, what is the net value added that is coming from that activity? Now what you find is that a surprisingly high proportion of activities in most businesses and government operations today do not add value at all. In fact, they add value negatively. Just today we were interviewing somebody from Texas Instruments who was describing a situation in which there was a business model with 200 activities, and 160 of those activities could be eliminated because they didn't add value.
One of the things that's happening today is this elimination of non-value-adding processes. Karl Marx was quite right when he drew attention to the tension between the social nature of labor and the private nature of capital, but that was then. And things have profoundly changed in that period. Even the boss today is probably not an owner. The CEO might have a good stock option plan, but he probably doesn't own the company. And most people who work in the company are workers. I guess today in the United States, 80% of those workers are white collar and typically work without supervision. That means that large numbers of processes that actually, or activities within processes that existed for the purposes of verification, control, authorization, and so forth, now no longer have any useful purpose, even though they do have a cost. And what a lot of companies are doing to improve process cost at least, and in many cases cycle time as well, is simply to eliminate those processes. I spoke with a South African finance institution recently in London. They had examined a process with 200 activities and eliminated 160 of them. Just got rid of them. And I was surprised, and I've checked this with a number of people doing this kind of thing, and they said, well, you know, people's capacity for creating complexity is almost infinite. And yes, we're not surprised at all. We think those things might be possible in our own business.
Once we can associate value with the activities, even if it's only a rough subjective estimate, then that gives us the capability to say there are a whole lot of activities here which we really ought to eliminate, or we can bypass many of these activities by taking information from here to here, and there is enormous scope for that in most of today's corporations. Now, we may do that with formal techniques such as activity-based costing, or we may do it with much less formal techniques in which we're making a subjective estimate of the net added value. So we talk about NAVE, net added value estimate.
In business reengineering, one of the challenges is to look at a value stream and a current rendition of a value stream. In other words, what work is being done today. And in preparation for re-engineering it, to say, all right, where is the value that the customer is experiencing? Where is that value being added within that workflow? And secondly, where is the cost that is involved with this value stream? There aren't any value meters around a corporation. In other words, everybody has their perception of what the linkage is between what they're doing and the value to the customer. So what the team has basically got to do is come up with a subjective evaluation of where the value producing elements probably are today. And if they've been doing activity-based costing, they can associate cost with the work steps, but many companies really don't have activity-based costing. They have allocated costing, so that they also have to estimate where the cost is. Personally, I think the estimation is fine, because the people that are in the business reengineering task force really have a pretty good feel for those processes, so their judgment about value and cost are accurate enough for the preparation process that we're talking about. There needs to be a focus on only doing those things that deliver value, or those things that are absolutely necessary to maintain some degree of order within the corporation, and eliminating all of the things that maintain functions and maintain existing organizations, which fundamentally have no value.
When we're doing business redesign, we'd like to have tools which enable the business people to model and redesign their own enterprise, but then, as we were saying, take that into a greater level of detail where the model becomes executable. So at the highest level, we want a model where the business people can show the activities and the workflow, and if the IT people model all of the activities, they usually get it wrong, and this is why we'd like the business people to model the activities in an enterprise. But then we'd like to take that into a greater level of depth. So take the workflow diagrams and the activity diagrams, and then add to that a representation of the business policies and rules, link it to a data model, and then we've got a model of the business which is executable and from which we can generate code. And when we can generate code, then we can simulate the business, and we can redesign it. We can try out lots of different alternatives, simulate the effect of different alternatives, generate spreadsheets from that, and the situation I think we're going to get to by the second half of the 1990s is that we are able to have tools which employ information engineering and rapid application development, so that we can model a business, describe the business policies, redesign the business, get the design which makes sense, and then make that model executable, so that from the business policies and rules we generate design and then generate code. Now, the implication of that is that when the business people then want to change their policies, which they're likely to want to do all of the time, we can take that change in policy and simulate its effect to see whether it's good or not. But very important, when they want to change the policy, we can, to a large extent, automatically change the code which implements that policy. Now, once this happens, it's going to give us an entirely new way of running businesses. So in the 90s, we are going to see a very dramatic change in corporations. And there's not much doubt that that is going to happen, because they, in Japan, have got very efficient business processes. The rate at which corporations are building up in the Pacific Rim countries, I've just come back from Korea, it's almost frightening, the speed at which they are developing businesses which can take business away from the West. So the 1990s is going to be a decade in which we're very much concerned with whether corporations survive. So we want the capability to be able to model the business, redesign the business. We want the business people to be able to visualize the business as effectively as possible. And the question which we're really asking on this tape is, have we yet found the best techniques for visualizing the enterprise, simulating the enterprise, representing the business policies, and creating models of the business which are executable models, so that we can drive those into code generation. And the capability to do that, I think, by the time we get to the end of this decade, is going to be something which strongly affects whether corporations will survive or not.
The more technology really is part of invention that is changing the basics of industry, the more we can be sure that 50% of companies will disappear.
The key for the future is information. That's the way we will differentiate ourselves and the way the leading companies will differentiate themselves.
Never before has it been so important to reinvent the corporation as today, partly because of technology, all manner of new technologies, which cause you to want to do things differently. And in reinventing the corporation, you've got to completely fuse the business considerations with the technology considerations. Corporate survival. Not long ago, Time magazine had a front cover asking the question, can General Motors survive? So being able to visualize an enterprise and redesign it is vitally important for the 90s. And this gives a whole new role to the IT organization. And in my view, the IT organization in most corporations needs redesigning today. So there's an upper level and a lower level to it. The lower level builds systems and implements networks and is concerned with all the complex technology. And the upper level is concerned with enterprise engineering and business process redesign. And the people who are in the upper level, one of the selection criteria for picking them is that they must absolutely talk the language of top management and be credible to the CEO of the business. But they do the business redesign, and then they create models of the enterprise which are executable, and so the systems builders below them are skilled with the case tools, information engineering, rapid application development, the building of complex networks, client-server technology, and so on. So, very important set of subjects here, and we're really asking the question, have we got the capability to visualize an enterprise in such a way that the business people will like it and understand it and give us the capability to create enterprise models which are executable. Because as that happens, we're going to see a maturing of IT so that IT will become absolutely fused with the design of the business. And that fusion of technology and the design of the business is essential for the future running of corporations.
And that takes us to the end of the 4th hour. We'll take a short break, and then we'll be back with questions. Please continue to fax your questions in. We'll be having I expect, lively discussion. Thank you.